How can two smooth, rigid steel surfaces generate enough grip to move that much mass without rubber tires? And if friction is so limited, why do locomotives not simply use tires like cars do? Inside every modern freight locomotive, a chain of powerful machines works in concert to turn fuel into motion. It starts with a diesel engine, often running at over 4,000 kilowatts, enough to power a small neighborhood. This engine does not drive the wheels directly. Instead, it spins an alternator, producing electricity that is then routed through a set of inverters. These inverters precisely control the current sent to 6 traction motors, each one mounted on a separate axle. The result is a system that can deliver enormous torque, especially at low speeds. Unlike a car engine, where torque peaks in the middle of the rev range, electric traction motors reach their maximum pulling power almost from a standstill. For a locomotive weighing over 200 tons, this means there is more than enough force available to start a train weighing thousands of tons rolling from rest. The alternator inverter setup allows for fine-tuned control, matching the power output to exactly what each motor and axle can handle without overwhelming the steel-on-steel contact. Even with all this muscle, the motors themselves are never the bottleneck. The real limit comes later, where the wheel meets the rail. But in terms of raw torque, the diesel-electric system is built to deliver far more than the wheels can actually use. This surplus is intentional, ensuring that the locomotive is always ready to push the boundaries of traction if only the rails will allow it. If you are fascinated by the hidden machinery that keeps the world moving, consider subscribing for more deep dives into the engineering beneath our everyday lives. The real test for a locomotive's muscle isn't just how much torque the motors can deliver, but how much of that power can actually reach the rail. The answer comes from a simple equation. The maximum tractive effort equals the coefficient of friction, mu, times the weight pressing down on each axle, what engineers call the normal force. For steel wheels on dry steel rails, mu usually hovers around 0.3. That is not much compared to rubber on asphalt, but it is enough when you are dealing with massive weights. Take a standard heavy freight locomotive with a 30-ton axle load. Multiply that by gravity, and you get about 294 kilonewtons pushing down per axle. With mu at 0.3, the adhesion limit is around 88 kilonewtons per axle, just under 9 tons of usable pull before the wheels start to slip. With 6 powered axles, that is a total of 528 kilonewtons, or roughly 54 tons of continuous tractive effort, right in line with what modern locomotives deliver day in and day out. But there is a catch. Adding more weight would boost traction, but it would also push the rails, bridges, and track beds past their design limits. That is why most countries cap axle loads at 30 tons. To move even heavier trains, railroads do not just build bigger locomotives, they add more of them, spreading the load across dozens of axles. This balance between available grip and infrastructure strength is what keeps the whole system moving safely and efficiently. Underneath the thunderous weight of a freight locomotive, something astonishing happens at the point where each wheel touches the rail. All that mass, 30 tons per axle, rests on a patch of steel barely bigger than a coin. The contact area between wheel and rail is usually just 1 to 2 square centimeters, shaped not as a perfect circle, but as a flattened ellipse. This tiny patch is called the Hertzian contact area, named after the physicist Heinrich Hertz, who first modeled how curved surfaces press together. The numbers are almost hard to believe. A single wheel set can carry more than 100 kilonewtons, sometimes as much as 250 kilonewtons. Yet all of that force is squeezed through a patch smaller than your thumbprint. The result is a contact pressure that soars into the range of 1,000 to 1,800 megapascals, 10,000 times atmospheric pressure. That is the kind of stress you would find inside a metal forging press, not out in the open air. And yet, both the wheel and the rail survive. flexing elastically with each rotation, then springing back into shape. Every time a locomotive starts to move, these tiny ellipses must grip the rail just enough to transmit the pulling force without slipping. If the force gets too high, the steel does not suddenly lose contact. It begins to slide microscopically, a process called creep. Before that happens, the patch acts like a microscopic handshake, the weight above, the rail below, and a sliver of steel in between, quietly holding back thousands of tons. This delicate balance sets a hard limit on how much weight each axle can carry and how much force can be used before the rail or wheel starts to wear out. Push too hard and the steel begins to deform, accelerating fatigue and wear. That is why railroads carefully control axle loads and spread the weight across multiple wheels. The entire system depends on these hidden patches, where physics and engineering meet in a silent test of strength. At the heart of every locomotive's grip on the rails lies a razor-thin margin between motion and mayhem. The secret is neither brute strength nor luck, but a phenomenon called creep, a controlled microscopic slip between wheel and rail. When a locomotive pulls a train, the wheels do not roll in perfect sync with the rails beneath. Instead, they turn just a hair faster, slipping by about 3% at the peak of usable traction. This is the sweet spot. Too little slip and the locomotive cannot deliver its full pulling power. Too much and the wheels spin helplessly, wasting energy and risking damage. The relationship between traction and creep forms a curve that rises quickly, peaks at roughly 3% slip, then drops off. Beyond this peak, the steel-on-steel interface cannot hold, and the wheels start to slide uncontrollably. So the challenge is to keep the locomotive operating right at the top of that curve, maximizing grip without crossing the line into chaos. Modern locomotives rely on a web of sensors and a lightning-fast control loop to walk this tightrope. Wheel speed sensors on every axle feed data to the onboard computer, which calculates the exact slip ratio in real time. If the system detects that creep is drifting above the optimal range, it cuts power to the traction motors in milliseconds, about 20 milliseconds. PID algorithms, the same kind used in industrial automation, constantly adjust torque to keep the wheels riding the very edge of adhesion. This control is not just fast, it is relentless. Every 20 milliseconds, the locomotive's brain recalculates, comparing commanded torque to measured slip and making micro adjustments to stay glued to the peak of the traction curve. Telemetry streams record slip percentages, torque commands, and rail temperature, helping engineers fine-tune performance for every route and weather condition. By surfing this narrow band of controlled creep, freight locomotives extract every ounce of grip from their coin-sized contact patches, moving thousands of tons with the bare minimum of wasted effort. Railways face a moving target when it comes to traction. Even the most advanced control systems cannot overcome the sudden collapse of grip when the rail is contaminated. A thin film of oil, a layer of wet leaves, or dust from a dry summer can drop the coefficient of friction below 0.10, less than a third of what is needed for reliable starts. In those moments, all the electronics in the world cannot help. The wheels spin and thousands of tons grind to a halt. Old-timers still recall the 1998 Sierra Nevada stall, when a freight train lost all traction after a rainstorm left the rails slick with leaf mulch. The solution then and now is sanding. Modern locomotives carry hoppers filled with fine, dry sand and deploy it automatically the instant sensors detect excess slip. Sanding boosts the grip just enough, raising MU by up to 0.12 for a few seconds so the train can claw its way back into motion. The system responds in less than a second, a mechanical fix for a physical problem that software alone cannot solve. Switching from steel wheels to rubber tires might sound like an easy way to boost traction, but the numbers tell a different story. The rolling resistance of a rubber tire on steel is about 10 times higher than that of a steel wheel on steel rail. For a 200-ton locomotive, that means an extra 30 to 50 kilonewtons of drag, enough to demand several more liters of fuel for every kilometer hauled. Over 1,000 kilometers, the wasted energy adds up to several megajoules per ton, mostly lost as heat in the tire itself. Rubber's higher hysteresis means more of each revolution is converted into heat, quickly raising tread temperatures and forcing the use of complex cooling systems. Wear rates tip the scales even further. A heavy locomotive running on tires would grind away half a millimeter of tread every 10,000 kilometers, requiring frequent replacements. Steel wheels, by contrast, lose only a fraction of that and can be reprofiled many times before reaching the end of their service life. The maintenance burden for tires would be overwhelming. Thousands of pounds of rubber changed out every few months, with each swap demanding heavy equipment and extra labor. Instead of adding friction, railways are engineered to minimize it. The low rolling resistance of steel on steel is the hidden ingredient that lets a handful of locomotives move mile-long trains across continents with unmatched efficiency. The trade-off is deliberate: less grip, less waste, and far less wear. Steel wheels carry freight because physics demands efficiency, not brute grip. Each train is a real-world proof. When engineers tune adhesion and rolling resistance, infrastructure moves farther on less. That principle drives not just railways, but every system shaping our world. Subscribe for more stories behind the engineering you rely on.